Hi everyone, thanks for tuning into my talk. I'm just going to try to share my slides. Okay, very good. Hopefully you can now see my slides on screen. Hi everyone, my name is Ashley Montanaro. I'm a member of the School of Mathematics at the University of Bristol. I'm also a co-founder of the quantum software startup Phasecraft, whose goal is to get the most out of near-term quantum computers. But today I'm going to be focusing on some work on the academic side of my job on quantum algorithms for constraint satisfaction and optimization problems. So the work I'm going to be talking about today is primarily presented in the three papers whose archive links you can see here on the screen. So slightly differently to some of the talks I think you're going to see here in this workshop, the projects I'm going to talk about, it will become clear, are suitable for sort of long-term fault-tolerant quantum computers rather than nearer-term, noisy, non-fault tolerant quantum computers. Also, the algorithms I'm going to be discussing are ones which are designed to exactly solve some constraint satisfaction and optimization problems. So here the goal is that we have some hard CSP, some hard constraint satisfaction problem, or some hard optimization problem, and we want to solve this problem exactly, but we're perhaps prepared to pay exponential time for this. So we accept we won't be able to do this necessarily efficiently, but we want to do it as efficiently as we can, even if that means we might need to wait for time exponential in the problem size. Our goal is to get that exponential time down to be as low as possible. And what I'm going to talk about today is ways in which quantum computing might be able to help us achieve that. Okay, try to go to the next slide. Okay, so as I just said, we want to exactly solve hard CSPs, hard optimization problems. And the sort of most famous algorithm, I guess I would say, in quantum computing for addressing this task is Grover's algorithm, which goes back a long way now. And this algorithm allows any constraint satisfaction problem with n solutions to be solved in about square root of n time. So we get a square root speed up compared with classical exhaustive search over the solution space. And we can also apply this algorithm to solve optimization problems in about square root of n time as well. So what I mean by this is that we want to find the solution, or the allowed input, let's say, that has the lowest possible value of some objective function. So we want to minimize some cost over all of the possible solutions. And Grover's algorithm, or sort of slight variation of it, allows us to solve this task in about square root of n time 2. So we get a square root speed up there as well, compared with classical exhaustive search over all of the solutions and checking their objective values and outputting the minimum. But there are a lot of classical algorithms that people have been working on for many years, which are much more efficient than these algorithms in practice. So if we have some constraint satisfaction problem that has some structure to it, we may be able to solve it in time that's better than just exhaustively searching over all of the solutions. We might be able to use this structure to do things that are more interesting than completely unstructured search. And what I'm interested in talking about today is how we can use this kind of structure to get an advantage over just pure Grover's algorithm for just solving the constraint satisfaction problem in a totally unstructured way. Okay, and in particular, what I want to talk about is firstly a quantum algorithm for speeding up classical algorithms that are based on the technique of backtracking, which I'll introduce in a minute. I should say everything I talk about today is reported in papers on the archive, and I'm just going to give the archive links to the various papers that you can search for and find if you want to learn more. So this quantum algorithm for speeding up backtracking, we can apply it to speed up so-called branch and bound algorithms. So this is a way of, roughly speaking, using the technique of backtracking to efficiently, or relatively efficiently, solve optimization problems. This is a very prominent and well-studied technique classically, and we can also speed this up with quantum algorithms. And also, the final thing I'm going to talk about is the sort of gory details of what is the exact complexity of the quantum algorithm when we calculate it in detail. Once we actually work out all of the gates and operations that we need in the circuit, can we figure out what the precise runtime of the algorithm is going to be? And do we still see an advantage over classical algorithms? And it turns out that we can do this calculation, and I'll talk about these results too. Okay, so first I want to introduce this technique known as backtracking, which I think will be very familiar to many of you who are experts in solving CSPs. But I'm going to introduce it for everyone else who might not be. And this algorithm is perhaps nicely introduced in the context of an application, which is going to be coloring, graph coloring. And again, this is something that's probably very familiar to many of you, but just to introduce this quickly. In this problem, we imagine that we have a graph which has some vertices and has some edges. And we want to assign a color to each of the vertices, picked from a palette of a certain number of colors. Here, perhaps 3 colors, red, yellow, and blue. And we want to assign a color to each of the vertices such that no adjacent vertices, no vertices that share an edge, have the same color. So we can see here that this is a valid coloring of this graph because no vertices that are next to each other have the same color. Okay. And what we want to do is we want to determine if a given graph has a valid coloring or of a certain number of colors or does not. And this problem turns out to be very challenging. It's NP complete, which is unfortunate because it has a huge number of direct applications, including tasks such as allocating registers in compilers, scheduling tasks, assigning frequencies in wireless networks. Many of these reduce to graph coloring. And as it's NP complete, in fact, there are many other problems that can also be expressed in this way. But our best algorithms for this problem run in time that's exponential in the size of the graph in the worst case. But it turns out that a very simple approach to solving this problem is often quite good in practice. And this is an approach that's known as backtracking, though we could also call it trial and error, because it sort of corresponds to trying something, and then if it doesn't work out, changing it a bit and continuing and seeing if it gives you a good route to a solution. Okay, so let's talk about how we could try and color this graph that we see here with just 4 vertices by backtracking. So it's perhaps easiest just to go through this process and we'll see how the algorithm works just from this example. Okay, so firstly, imagine we've got this graph. It's got 4 vertices. We want to color it with 3 colors. And what we're going to do is we're going to take things vertex by vertex. We're going to start out with one of the vertices and we're going to try assigning it a color. Now, we have 3 different possible colors that we could use in this problem that we're going to try today. We have red, yellow, or blue. So we could try assigning the highlighted vertex red or yellow or blue. So, okay, let's start by assigning it red. And things are all fine so far. So let's go on to the next vertex on the bottom right. So again, this one we could assign it red, yellow, or blue. But we can see already that we don't want to assign it red because there's a vertex next to it that's red. So our only options without causing a conflict already are yellow or blue. So let's try assigning it yellow this time. And okay, that's fine. We can have red and yellow. Now let's move on to the next vertex, which is the highlighted one here, the one on the top right. Again, we have a choice of red, yellow, or blue, but now we can see that if we assign it red or yellow, these are both conflicts because they clash with one of the neighboring vertices. So the only option that we can assign it now is blue without violating one of these constraints. Now, finally, we have the last vertex, again, choices of red, yellow, or blue, but here, again, there's only one choice that we can assign this vertex, which is yellow. So we have to go for that one if we want to have a valid coloring. So what we can see here is that we found a valid coloring of this graph with 3 colors, while only exploring a fraction of the total solution space of all of the possible colorings. So in general, like if we were trying to color a graph with n vertices and we have, say, 3 colors, there are 3 to the n possible colorings that we could try if we were just searching over them in a completely unstructured way. But the hope is that using an approach like this backtracking, by ruling out bad colorings early on, we can cut down the solution space a lot and explore a space that's much smaller than size 3 to the n. So this approach is very simple. You can apply it whenever you have a problem where you can check whether a partial solution is valid before you've created a whole solution. And it turns out to actually be very practically relevant classically, because it turns out that a lot of problems you can actually solve relatively efficiently in practice using this kind of approach. So what I'd like to talk about next is how we can try and accelerate this using a quantum computer, this sort of very general backtracking approach. And a way that we can think about this very generically is as a problem involving searching in a tree. So we imagine that we have a tree, which I've shown here on this slide. This is the tree of partial solutions, like we saw on the previous slide. So if I go back, so we can see we have this tree structure that the algorithm is exploring. And this tree is supposed to abstract away this notion of exploring this tree of partial solutions. And we imagine that we're looking for a so-called marked vertex, one which is a good vertex, let's say. And we're starting at the root of the tree, this yellow one here. And all we can do at each step is move around in the tree to a neighbor and check whether the neighbor is marked or not. So we imagine these green ones are the sort of solutions that we're looking for to our constraint satisfaction problem. And the yellow one is where we start. And the tree has some kind of complicated structure which isn't known to us in advance, but we can explore it, and we're looking for a green vertex. And if the tree has t vertices, then classically, using an algorithm like depth first search or something like this takes time about t. So it takes about t iterations to find a marked vertex using this method. But it turns out that using an algorithm of Belov's from 2013, there's a quantum algorithm that can detect existence of a marked vertex in a tree with t vertices that has depth d, using order square root of t times by d queries. So if d is very small compared with t, then this is a square root type speed up. And when I say queries here, I mean a query is looking at a vertex and saying, is it marked or not? Is it a good vertex? And also, what are the neighbors of that vertex? So a query allows us to determine if we should stop at a given vertex because it's one we're looking for, or if not, then what our neighbors are that we can move to. Okay, so this algorithm of Belov's allows us to get a square root type speed up like Grover's algorithm in a way, compared with the classical algorithm of exhaustively searching through the tree of partial solutions. And Belov's algorithm is based on a so-called quantum walk in the tree. And this is a quantum analog of a classical random walk. So classically, a way we could try and solve this problem is starting at the top and just moving around randomly through the tree. So maybe try to go left with 50% probability, right with 50% probability, continuing on through the tree in this way, always sort of going down perhaps, but always going left or right with 50% probability of each, in this case, if it's a binary tree. That may not necessarily be quite the best algorithm classically, but it's a pretty good algorithm for finding a marked vertex. And using a quantum computer, we can accelerate this with a so-called quantum walk, which gives us this square root advantage. Okay. And we can apply this sort of directly, this method, to solving backtracking problems. Because if we have an algorithm based on backtracking that's solving a problem with n variables, then we can see this as exploring a tree that's of size t for some t, which we don't necessarily know in advance, and depth n, where again n is the number of variables. And if we use this algorithm of Belov's, then we get a result that says that there's a quantum algorithm which finds a solution to a constraint satisfaction problem solved by a classical backtracking algorithm, or outputs that one doesn't exist in time square root of t times by some terms that are polynomial in n. And this poly n is a bit worse than the square root of n that we would have got just from Mello's algorithm. And this is because it takes into account the fact that at each step you're doing some classical processing to work out, okay, do I have a solution at this point, or have I violated some constraints, or or what are the neighbors of the current vertex I'm at in the tree? So all of these I've sort of rolled together into this poly n, and we get a quantum algorithm which has a square root advantage compared with the classical algorithm in terms of the size of the tree, at the expense of some of these lower order terms here, because we normally think of the size of the tree being being exponential in n. So this is the dominant term in the complexity. Okay, and this algorithm has since been improved by some other authors. For example, Ambinas and constraint improved this to have a complexity which depends only on the number of vertices actually visited by the classical backtracking algorithm rather than the entire tree, which is what my algorithm algorithm's running time was based on. And Jarrett and Wan also had an improvement in terms of expressing the runtime of the algorithm in terms of an effective resistance parameter rather than the ones that mine was expressed in. Okay, and this backtracking approach in the quantum algorithm can also be generalized to solve optimization problems. And this approach is based on a technique known as branch and bound. And again, I think this is very familiar to many of you, but this technique is applicable whenever we have a branching procedure that splits some set of potential solutions into subsets, and a bounding procedure that gives us a lower bound on the cost of any solution in a subset. So to be clear, here what we're looking for is a solution to some problem that has the lowest possible cost, right? So some potential solutions may not actually be valid solutions, or some of them are valid solutions, but they are costly, and we want to return the solution that has the lowest cost. And we've shown it here on this slide via a diagram. And we can imagine here that each vertex in this tree corresponds to a subset of solutions, or potential solutions. And within each subset, we have some solutions. And we also, for each subset, have associated a cost with it. And this cost is basically a lower bound on the cost of any solution in that subset. So at the top here of the tree, we have the set of all solutions. And this, we imagine, has a lower bound of cost 1 on it. So all we know in advance is that there's a lower bound of cost 1 of the solutions in this subset. So what this means is that all solutions in this subset have cost at least 1. And then as we go down the tree, this lower bound increases. And then right at the bottom, the leaves of this tree, these are the actual solutions. And some of these are not real solutions, they're not valid, they have cost infinity. And others have a cost, an integer cost here. And what we're looking for is the solution that has the minimal cost. So here, 4 is the solution with the minimal cost. And each of these vertices above this is specifying subsets of the solutions, and it's associated with some lower bound on the cost of these solutions. So for example, here we have 2, which is a lower bound on 7 and infinity. Here we have 3, which is a lower bound on 6 and 4. And so on, we sort of continue from there. And the point of these lower bounds is that they enable us to sometimes throw away parts of the tree. For example, if we've already explored this vertex here, this solution 4, and so we know, okay, this is a solution, we're looking for one that has maybe a lower cost than that. And if we find 5 here, when we explore this part of the tree, then we know that there's no point in exploring these vertices here at the bottom, because 5 is higher than 4. So everything below 5 in this part of the tree is going to be more costly than 4. So as we already have a solution with cost 4, there's no point in proceeding further. So in this way, branch and bound enables us to get more efficient algorithms by throwing away big chunks of the tree of potential solutions. And we can see this as a variant of, or a generalization of, backtracking, because in backtracking it's the same, only the cost bounds are always either like 0 or infinity. So in backtracking, all we know is that, okay, we can throw away a subset of the solutions, we don't need to explore it further, or we should continue to explore it further. And so branch and bound is a generalization that is a bit more complex. And it's an interesting question whether we can speed this up using a quantum algorithm. And it turns out that we can. And we imagined that we have to start with some classical algorithm, which we're going to keep totally general. It's just a generic classical algorithm. And it solves some optimization problem using these branch and bound procedures I introduced on the previous slide, T times. So it solves some optimization problem, and it uses these sort of oracular, sort of abstract procedures on the previous slide, T times. Then we get a quantum algorithm that solves the same problem using these procedures square root of T times up to some lower order terms. So in this case, the lower order terms scale with T, and they also scale with the number of variables, just as before. So there's some sort of logarithmic terms in T and also some polynomial terms in the number of variables. Okay, and I'm not going to say too much about the quantum algorithm, other than just to mention that it is based on the use of this backtracking algorithm that I previously discussed as a subroutine. So roughly speaking, a way that we can try and use backtracking as a subroutine to solve branch and bound problems is that we could imagine taking this branch and bound tree on this slide and somehow turning this into a sort of decision problem, a sort of yes/no problem, by saying by having a threshold where we say, okay, is the cost of a partial solution, is the cost of a solution within a subset lower bounded by some threshold or not? So, for example, we could say, okay, is there a solution with cost at most 2? And if we had this threshold, then when we were exploring the tree, we would continue to explore this 1, and this 2, but we wouldn't continue to explore this part of the tree down here because it's all solutions with costs bigger than 3. So by sort of continually updating this threshold, we can either keep or throw away parts of the tree. And this is a way of applying the backtracking algorithm to explore the tree efficiently. So we start up with a threshold. We say, okay, can we find a solution with cost below that threshold? And if we can't, then we increase the threshold and we try and find a solution with cost below the new threshold. But there are a couple of delicate points here. So in particular, how do we pick the threshold? And we can do it via an approach using binary search, but there are a few technical details which make it a little bit delicate, but nevertheless, it is possible to do it. And we can get an efficient quantum algorithm for branch and bound 2, which gives us a sort of square root speed up compared with the classical algorithm. Just to mention a particular problem to which this can be applied, it's to find ground states of the Ising model. So this is maybe something of interest to physicists in the audience. So this is a very nice problem originally coming from physics, where we have a sequence of n variables that are associated with plus or minus 1. So these are so-called spins. So these are the z's that they're each associated with plus or minus 1. And the problem instance is specified by some coefficients aij, which are real numbers. And we want to choose an assignment to the variables zi, such that we can minimize this overall expression here. So we have some sort of matrix of coefficients aij, and we want to minimize this overall sum here, which is a sort of energy of the physical system specified by these aijs. And this, again, is a very sort of well-studied problem. It's NP complete, and it is it's applicable in many cases. In particular, it's effectively equivalent to a combinatorial optimization problem called MaxCut. Okay, and one particular case which has been studied in the physics literature is something called the Sherrington-Kirkpatrick model, which is, I guess, in some sense, a sort of toy version of this problem, where these AIJs are random and they're normally distributed. So they are normal, independent, normal random variables with the same mean and variance. And if we want to find the lowest energy assignment to these ZIs, then we can do this by exhaustively searching over them in time 2 to the n. Or if we have a quantum computer, we can use Grover's algorithm and get 2 to the n over 2. But it turns out that applying this quantum backtracking / branch and bound approach, we can prove that we can get a better runtime than this, which is 2 to the 0.226 n. And empirically, it seems that the algorithm's runtime is better still based on some experiments. But the nice thing about this is this does beat Grover's search for this particular problem. So it may well be that, in fact, we can do better than this still, though we don't necessarily think that we're going to get better than a square root improvement on competitor classical algorithms. Okay, so the last thing I want to talk about is, will this approach based on backtracking or branch and bound, will it really yield a quantum speed up in practice? So if we have a real quantum computer, then it may actually run somewhat more slowly than a classical computer in terms of clock speed, because this is new technology. The quantum hardware is still relatively limited, and it's not running at the same speed as our sort of super fast classical computing hardware that's been developed over many years. Also, there are a lot of overheads that go into quantum algorithms, in particular to do with fault tolerance. So the algorithms I've talked about here are very much ones that will run on a fault-tolerant quantum computer long-term, rather than runs that will run on a near-term quantum computer. And in fact, what I'll show you in the next few slides will very much highlight that that is the case. So we need to take into account the costs for fault tolerance and all of the other sort of overheads that go into actually running the algorithm. And for example, we need to actually calculate the real complexity rather than all of these big O notation type complexities that I've showed you. Because it may be that these constant factors are large enough that to see a speed up, we need to go to very, very large problem sizes, which are actually still infeasible to address. So in order to address all of these questions, we need to actually do some calculations and work out what the true complexity of backtracking or branch and bound is. And we did do this for the backtracking algorithm. And we looked at this problem of graph coloring that I previously mentioned, and we tried to work out its complexity in great detail. So to start with, we worked out the precise quantum circuit complexity of the algorithm, so the number of time steps that the algorithm needs. And we found some sort of circuit optimizations to try and get this down as far as we possibly could. We then had to work out what the algorithm's runtime was actually likely to be when we look at particular problem instances. And this is quite a challenge to do because by its very nature, we want to apply this algorithm to instances which are too hard to solve classically, or certainly very challenging to solve classically, which means that it's difficult to estimate what the runtime is going to be of the classical algorithm for solving the problem, which is what we need in order to work out the runtime of the quantum algorithm. Because the quantum algorithm's runtime, at least in this sort of abstract sense, just looking at the number of time steps before we work out how long these time steps take, that classical algorithm's runtime governs the quantum algorithm's runtime, and it may be hard to estimate. But the way that we did it, or we got around this, is that we looked at random problem instances, so random graphs, and looked at the complexity of coloring these, with the hope being that we can then draw a plot, basically, of the complexity of the algorithm as the problem size increases, to try to work out what the complexity will be when we go beyond sizes that we can actually address classically. And then finally, once we've worked out the true runtime of the algorithm, we, in a sort of abstract setting, depending on the problem size, we then calculated what this actually translates to physically for various choices of hardware parameters for the quantum computer. So we can actually get a sort of real world running time of something we can measure in like seconds or minutes or days, something like this. And of course, all of these steps involve a lot of assumptions, but at least they're a way that we can go from something very abstract to something where we get concrete complexity bounds. And finally, we compared this against the performance that we might expect to see from a classical algorithm that's been studied in the literature. We chose a branch and bound based one called DSATA, which is a nice sort of exact exponential time algorithm, which is a valid comparator. There may be other algorithms which are also strong performers, but this is one which, at least in the literature that we're aware of, is kind of up there with the best classical coloring algorithms for dense random graphs. At least it was a few years ago. So it's a sort of valid competitor to look at with the quantum algorithm. Okay, so in order to work out what the overall cost is of the quantum algorithm when we're really running it on hardware, we need to understand the effect of error correction. And we chose to use the surface code for this, which is a very well studied and prominent approach for quantum error correction. And in particular, people have worked quite hard to optimize its complexity, which is nice. And then once we've worked out the runtime and space usage of the overall quantum algorithm, we then convert this to real world runtimes based on various regimes that correspond to different parameters that the quantum computing hardware might have. So this is what I'm going to show you over the next few slides, what the final times are that we eventually calculate. And for these to make sense, I should show you what the assumptions are we make about the quantum computer. And some of the key parameters that go into these are the time it takes to do measurements. And this is important because in the surface code and many other fault tolerance schemes, most of what you're doing in the algorithm is actually doing measurements. So the time it takes to do measurements is important. And we also need to know how long each 2-qubit gate takes. This is a sort of elementary logical operation in the quantum computer, and we need to calculate how long this takes. We also need to make some assumption about what the error rate is of these gates, because that goes into the overheads of the fault tolerance scheme. Okay, so these are all of the assumptions on this slide. Realistic is not far off what we have in experiments that are in the lab today. Plausible is one order of magnitude better, and optimistic is another order of magnitude better still. So experts may definitely quibble about whether these words and these complexities are believable, but at least they're yardsticks, some simple yardsticks, which enable us to get some final bounds. Okay. So I just want to summarize the results that we saw. So firstly, in the most optimistic regime, this optimistic column, we might see speedups of greater than a factor of 10,000 or so compared with a standard desktop PC. And I want to clarify that this is for problems that we can solve in at most 1 day on the quantum computer, because as the size of the problem increases, the quantum speedup will also increase, but it's probably not realistic to say, okay, we're happy to leave the quantum algorithm to run for a year to solve a graph coloring problem. We probably are happier to put an upper bound of a certain amount of time that the quantum computer needs. And in this case, we put an upper bound of 1 day. And within this, this time budget, we might see speedups of the order of 10,000 times or more compared with a standard desktop PC. But the speedup gets a lot less if we look at quantum hardware that's available today, or parameters corresponding to that. And an important point is that if we try to additionally take into account the cost of doing the classical error correction processing that we need to do at the moment, then this speedup disappears. So what I mean by this is that to do fault tolerance in a quantum computer, we need to do a lot of classical processing too, to do the error correction steps. And this comes with some cost. And we could instead use the classical hardware that's doing this error correction processing to do the graph coloring problem itself. We could use this hardware to solve the constraint satisfaction problem directly. So we ought to take into account the cost of actually doing the error correction processing, because otherwise it gives the quantum computer an unfair advantage. And also the number of physical qubits that we use is very, very large, e.g. like bigger than 10 to the 12. So as some of you may know, if you have a quantum computer that runs an algorithm based on fault tolerance, then it runs on a certain number of logical qubits, but these are implemented via a much larger number of physical qubits, which are the ones on the real device. And almost all of the physical qubits are used for fault tolerance. And in this case, we have very many of them if we want to achieve this sort of speed up. So this gives us a lot of motivation to come up with better fault tolerance techniques. Okay, so just to summarize these in tabular form. So if we look at these different regimes, realistic, plausible, and optimistic, here we've got on the table the largest problem size in terms of the number of vertices for a graph coloring problem that we can address in one day. The next few columns, the next few rows is just saying something about the complexities of the quantum algorithm, which may be not so interesting for most. But I guess the important points really are probably down here in the bottom rows. Like the second from bottom is the number of physical qubits that we need, which is of the order of 10 to the 12, 10 to the 13. And the last row is this speed up that we might be able to achieve. And in order to get a decent speed up, we sort of need to be in this optimistic regime here, and there the speed up is bigger than 10 to the 4 or so. And it's worth saying that we also did this calculation for solving Boolean satisfiability problems via Grover's algorithm, which is a simpler calculation and using backtracking. And the speedups turn out to be slightly bigger, in fact, because the quantum algorithm is simpler and somehow it's easier to sort of handle these constant factors which are causing us problems in this case. Subsequently to this work, there was sort of a similar project which achieved also some detailed complexity estimates for some other quantum algorithms and many different constraint satisfaction problems. This is by a team at Google and collaborators, and their bounds are similarly pessimistic, I guess it's fair to say, or perhaps even more so, because that they did not see a significant quantum advantage at all. But we use a slightly different model where we're assuming that the quantum computer can be much larger than they are. They put some restrictions on the size of the machine that they're looking at, whereas we were interested in, you know, if we're prepared to pay this huge penalty in number of qubits, how well can the quantum algorithm do? Okay, and as I mentioned, we should take into account the cost of classical error correction processing too. And the way that we do this is that we start out with the runtimes for quantum error correction that have been reported in a lovely paper by Delphos and Nickerson in 2017. And we then extrapolate this to more exotic, let's say, hardware platforms that may use special purpose hardware to solve quantum error correction processing efficiently. And just to show you a table with these results too, the important one here, I guess, is the last row, which is the one where we're implementing a number of quantum operations that's of the order that we actually need for the quantum algorithm, so of the order of 10 to the 20 operations. And if we want to do this, then the number of processor days that we need to solve this, to do this error correction processing classically, it's of the order of like 10 to the 16, 10 to the 13, or in the most optimistic case where we imagine we have a special purpose ASIC and made some assumptions about what sort of speed up this gives and so on. If we make this assumption, then we need about 10 to the 8 sort of processors working on this error correction processing. So this really kills off a lot of the quantum speed up that we saw before. In fact, entirely so if we make the assumptions on these slides. So what I think this shows us is that if we want to achieve a quantum speed up for problems like this, using these sort of exact exponential time algorithms, then we're going to need to have some improvements in classical and quantum fault tolerance algorithms. We're going to have more efficient fault tolerance schemes that don't have these big overheads with classical processing. Okay, I just want to mention some subsequent developments in this area. So building on these backtracking algorithms that I mentioned, they've been applied to some different problems, which is not surprising because classically backtracking is extremely widely applicable. For example, within lattice-based cryptography, people have used the backtracking algorithm to show that we can get quantum speedups for finding shortest vectors in lattices. So this goes into proving bounds on the hardness of solving cracking crypto systems using a quantum computer. In a paper with Moylet, myself, and Noah Linden, we applied this algorithm to the traveling salesman problem, which is a sort of very well-studied problem in classical computer science and combinatorics. And if we have a bounded degree graph, it turns out that there's some nice approaches based on backtracking for solving this problem, and we can get a quantum speed up of those. It's also been applied to exact satisfiability problems and in the general framework of constraint programming, in fact, by one of the organizers of this event. And this algorithm has also been implemented experimentally in classical simulation for graph coloring, when a graph with 4 vertices with 2 colors. So this is a very small scale implementation, but it's nice to see that this algorithm does actually work experimentally, at least in classical numerical simulation. So this is a very nice validation of this approach. Okay, so just to summarize what I said, we might be able to get a fairly significant quantum speed up for very common and also very practically relevant problems using an approach that's based on accelerating backtracking algorithms. So we may be able to achieve a square root type speed up over classical algorithms based on backtracking or branch and bound by using quantum algorithms and algorithms based on quantum locks. But there are a lot of challenges that we need to address before this actually becomes realistic. In particular, we really need to improve our fault tolerance techniques. Either that or have extremely low error quantum computers in order to be able to make these algorithms that I discussed really applicable on real quantum devices to real problems. And that's everything I wanted to say today. So thank you very much for listening to my talk. And I'm just going to stop the recording now. So thank you all very much.